Okay. So there are two transports, TCP and UDP. So we will talk about what are the design issues and how they are resolved, how we do multiplexing, many people or many applications, how do we do reliability, what is a flow control and how we do it, what is congestion control and how do we do it, and then UDP, TCP, all the details. So first, without going into TCP or UDP, all the transports have to worry about these things: multiplexing, error detection, flow control, efficiency, and retransmissions. So first of all, about layering, that most of the end systems have all the layers from physical to applications. I've shown 5, which you know that this is actually layer 5 through 7. So anyway, so the applications run on transport, on network, and then they are run on data link, they run on physical. And they send a packet which has application header, transport header, network header, data link header, and then maybe PHY header. And then you can see the packet on the wire with all these headers, right? When it goes to a router, which is an intermediate system, the router doesn't care for what application it is or what transport it is. It doesn't look at those headers at all. It looks at these 3 layers. It looks at physical, data link, and network layer. Okay. And as soon as it has looked at the network layer, it knows what to do with this packet. And then it puts either a new network data link and physical header, and then send the packet, or maybe even the old one, and send the packet forward. Other routers do the same thing. They just look at the 3 layers. And then when the packet goes to the other end, that is where all the layers are looked at all the way to the application. Is that clear? That intermediate systems work on the bottom 3 layers. The end systems need all layers. Okay. And so when the packet comes in, now let me ask you, if I were to look at the packet here, what would be the outermost header? What is the header? What is the first header and second header in the packet, third header, fourth header, fifth header? What are the headers? Can you think about what is the first header on the wire? Anybody? Physical layer, right? That's very good. Basically, the application thing is just inside. After the application, outside the application is transport. Outside the transport is the network and so on and so forth. So the physical layer headers comes in. The physical layer here looks at those 5 headers and decides what to do with this. It takes out the 5 header and then gives the packet to the data link. The data link looks at the data link header and then decides what to do with it. Takes out the data link layer and then header and gives it to the network layer. The network layer takes out the network header. But it doesn't then looks at the transport, it just looks at the network header and then decides that the network layer will say that it is going to whatever country or whatever address. Based upon that address, it puts a new header, gives the data link gives to the physical layer, they all put new headers and then the packet goes on. So the headers keep changing along the way. Okay. All right. So what does transport layer do? Transport layer does multiplexing and demultiplexing. So the TCP is being used by many applications. There is HTTP, there is FTP, and so on and so forth. All of these have to be put into one pipe. And so that is called multiplexing. When the packets come up from the wire, they have to be given to the right application. That is called demultiplexing. Error detection. But before we do anything with the packet, we have to see that the packet is good. Otherwise, you might give it to the wrong person, a wrong application. So error detection has to be done. Loss detection, we have to see that the packets are in order. If I send 4 packets and only 3 arrived, we have to know which one didn't arrive. And generally that is done by sequence numbers and ACK. So talking of the ACK, somebody had asked a question, what does ACK mean? ACK is short for acknowledgement. And every packet that is sent is acknowledged. So if I send you packet number 4, you will send me another packet which says, okay, I got packet number 4. That is called ACK4. That is called the acknowledgement for packet 4. Okay. And those of you who have used acknowledgement in the postal service, acknowledgement is a separate piece of paper that you attach to your mail. It goes to the recipient signs it, and then you get it back. Right? Registered mail. And that's very expensive. That's why most of us don't do it. But that is a possibility. So acknowledgement is ACK, right? And then loss and error recovery. Now, if you do find that there's a loss, what do? You have to retransmit it. Flow control. Now, the flow control is, if suppose you asked me for a terabyte file, and I send you the whole terabyte in 1 second, I have very fast network, and I could do that. But then you don't have that fast network, and you don't have that biggest disk. You just want to get it slowly so you can play it on the TV and then be done with it. You're not really going to store anything. So the flow control means that you send it at a rate at which I can consume. Flow control, just like on a water hose or water pipe, you control the rate. Who controls the rate? The receiver controls the rate. The receiver says, I cannot use more than 10 megabits per second. So even if you have gigabit link, forget it. Just send me at 10 megabit per second. So that is called flow control. That means ensuring that the receiver has enough buffers. Congestion control is different. Congestion happens on the highway. Congestion happens on the network. Okay? So the network wants to make sure that you do not just send a terabyte in a second. Okay? Receiver has no control over it. The sender actually has to just follow the rules. And so that is congestion control. Okay? And so ensuring the network has capacity and provides all function. By the way, my original research was on congestion control. I'm one of the original people who invented congestion control problems, and so on and so forth. Someday you can read it all up. But anyway, that is where I started my life. So the idea is flow control is different from congestion control. Flow control is done by who? Who controls the flow? Somebody must have heard I said something, and it's actually on the slide too. Who controls the flow in the flow control? Receiver. Who controls the flow in the congestion control? The network, the intermediate systems, not the end system. Okay? Because congestion is different than the flow control. Okay? Actually, before my time, people thought they are same. And the flow control was handled exactly the same way as congestion control. Anyway, so the protocol layers that we are going to talk about are clearly two, TCP and UDP. Both of them use IP, but there are many applications. So multiplexing and demultiplexing is done by the port numbers. Every application has a port number. So do you know what is the port number for web? 80. So when port number 80 comes in, it knows that it is going to the web. It is going to the web. That is the destination address, by the way. Coming from it could be any port. And so basically, let's say this is user 1 and this is the server which is serving web and DNS. This guy sends a web request. When the request goes out, the destination port is 80. DP. The destination port is 80. The source port. So every transport header has 2 ports. source port and the destination port. We will see in a minute why we need the source port. But the destination port is 80 and the destination address is as given here. So it goes to that address and then the TCP looks at the port number and says, oh, this is 80. I should give it to the web server. Then the web server gives a response and the response comes back to this host and it is given to who? So basically what the servers do is they exchange the source address to destination address and the source port to destination port. So when the response comes back, it has the destination address of 128.341, which is this computer. Okay, this was the source address before, now it becomes the destination address. This was the source port 3009. This becomes the destination port. So now when the response comes back, it is given to this process. This process could be doing anything. It doesn't have to be web or anything. It could be just any process that requested that. So only on this side there is standard. At the server side there is standard numbers. At the source side you can just use any number. Okay. It is used to get the answer back to you. So you see the source port is 3009, destination port is 80, the source address is this address, and the destination address is the server's address. When the response comes back, these things are interchanged. So the source port becomes 80, the destination port becomes 3009, source address is that server, and the destination address is the client. Is that clear? How the source addresses at each layer are interchanged in the IP layer and in the transport layer. This is the transport header and this is the IP header. Okay. Now there is this other guy. He is doing some DNS request. So he sends a DNS request and it comes back here to the DNS server, and the DNS server gives a response and it goes back. Now DNS uses UDP. And I don't have the port number for DNS, but let's just take any random port number 101. It doesn't matter really. It is not the right number. But anyway, so the destination port here would be what? With UDP, we'll put the destination port as 101 because it is going to DNS. And the source port could be any number. It could be even 3009. Okay. And the source address would be this address. And the destination address would be that. Okay. Now the packet will go here. Now the IP will know that it came from UDP. So there is some indication here that this came from UDP, which we'll see later on. So it knows that, so it will give it to UDP. And then the UDP will look at the port number and say it is port number 101. So I should give it to DNS. Okay. And the DNS will again do the same thing. It will interchange the source and the destination addresses and the source port and the destination port, and will come back to the same user, same process, same place. So many different users from many different computers could be reaching the same server. There is no mix-up because IP keeps the computers apart and TCP keeps the applications apart. Okay. You see how the multiplexing and demultiplexing is done? Multiplexing is many people coming and demultiplexing is getting out. All right. So UDP actually is the first transport protocol that we'll talk about, and it is very simple. So basically, the reason it is very simple is because there is no connection. All it does is multiplexing by a port. So it does have a port number, and it doesn't, and the error detection is optional. So maybe there is maybe it isn't there. It applies to pseudo header. So if there is a checksum, it applies only to the header and not to the payload. the payload is not protected. And UDP segment, if not used, it is set to 0. So we will talk about the checksum, and it says it is same as TCP. So we haven't talked about as to what does it mean to be the same as TCP. And then there is no error recovery, no acknowledgement, no retransmission. And it is used by protocols that don't care for any of these things, such as network management, DNS, multimedia. These applications can sustain loss. They work fine if there is a packet loss. And they are delay sensitive, but they want the answer fast. Okay, and if they don't get the answer, they have their own way to get it again. So this is the packet format. Basically, it's very simple. There is a source port, destination port, length, and checksum, if there is checksum, right? So if checksum is not there, it is just put to 0. So basically, and then following this is the rest of the IP packet. Now, I have simplified this a little bit because the actual packet format might come up later on. But anyway, so this is, I will stop right here. Next time we will talk about the checksum.